Okay, let's go over our practice test. Alright, the first thing you had to notice on this problem here is that I have kilometers here and my velocity is in meters per second. And that's one of the things with the AP test you've got to be careful about, is making sure you have agreement between units. So the first thing I'm going to do is I'm going to convert this to 3,400 meters. And I'm going to say, okay, well what I've got is I've got a jet here. This is jet A flying this way, and I've got jet B flying this way, and there's this much distance between them. Now what I know is jet A is traveling at 220 meters per second, and since it's catching up with jet B, I know jet B must be going slower than that. So remember, with relative motion, the thing is when they're separate, you subtract them. So if I have two separately moving objects, like two jets chasing each other, two cars coming at each other, something like that, a person chasing somebody, you subtract the velocity of one from the other, keeping in mind that you have to use a negative sign if one of them is moving in a negative direction. In this case, they're both moving in the positive direction. So what I'm going to find is 220 minus this is going to equal their net velocity. Now the net velocity is going to be found by using the equation. Since they're not accelerating, anytime we have objects that are moving without accelerating, we're going to use this equation. So the net velocity between them can be found by dividing the difference in the distance divided by the amount of time. So if I divide 3,400 by 85, what I come up with is 40. So what I get is a net velocity of 40. So that means that this jet here is going 40 meters per second faster than this one here. So basically, this minus this is going to equal 40, and that means it's got to be going 180. Now, and then the next one, we have a boat on a river. So they're not separate objects in the sense that the boat is being moved by the river. And since if one object is moved by the other object, in this case I have to add them. The way I remember that is if the boat is going in the same direction as the river, clearly I add the two. If you're running the same direction as the moving sidewalk, you add them. So when the two objects are one is moving the other one, you have to add. So in this case, what we find then is they're going in opposite directions. So I'm going to go ahead and make the river the positive direction, and I'll make the person the negative direction. And so since they are together, I'll add positive 3.2 and negative 1.8, and then that gives me the net velocity, and I have the change in distance. So I'm just going to swap the net velocity. I'm going to divide 25 by the net velocity, and that gives me this number here. Now the person on the ferry, this is another, this is where we have both objects moving together and separately. So let's just see if we can figure out how to do this next one here. Okay, so a person on the ferry riding bike towards the front of the boat. Speedometer on the bike only knows how fast the person is going relative to the boat. All right, and that says they're going 6. And now the ferry is pulling away from the dock, so the speedometer on the bike has no idea what the boat is doing, and the speedometer on the boat says it's going 5. Now since so let's just read this. How fast does the radar gun say the person's moving? Because the person with the radar gun is standing on the dock, and if you're standing on the dock, the motion of the boat carries the person away, and so does the motion of the bicycle. So I have to add those two motions together. So what I get is the bike is being moved by the boat, so I have to add those two together, and I get 11. How fast is the person on the bike approaching the front of the boat, dispersed to the front of the boat? Well, if the two objects are on the same moving thing, in this case the espresso stand and the bicycle, just like you and I are on the same planet, we ignore the motion of the planet is the easiest way to solve the problem. We're simply going to ignore the motion of the boat, and in which case she's moving towards it at 6 meters per second. Now, how fast will their distance change? How much will the distance change from the radar gun in 5 seconds? When I remember the radar gun sees both the motion of the boat and the person, so that would be 11 meters per second for 5 seconds, gives me a delta x of 55. And if the cyclist is 72 meters from the front of the boat, how long before she goes over the front? In this case, I have delta x, and here's my v. The motion of the boat doesn't matter in this case. It'll happen whether the boat is moving or not, and I get 12 seconds. For each of the following, determine if the acceleration is positive or negative. Well, let's see what I have in the first one. An object is thrown upwards, and it goes from going up at 30, so it's slowing down in the positive direction, and then it's speeding up in the negative direction. That's called negative acceleration. Now I have a car that's driving from the right to the left, and as it does so, it's getting slower and slower and slower. So it's slowing down in the negative direction. That's called a positive acceleration. Because remember, if you keep slowing down in the negative direction, you're eventually going to stop and speed up in the positive direction. That's one way of remembering it. Motorcycle traveling to the right, hits the brakes, ends up going. Well, I'm just going to use the first big kinematic equation. I'm going to say V equals V naught plus AT. And I'll simply substitute in, let's see, the motorcycle was traveling at, let's see, I want to know how fast it is, so I'm just looking for this. So here's my initial, here is my final, and here is my time, and I simply solve it for A. Now, keep in mind, well, you can do when you do your math. Alright, let's keep going here. Soccer player kicks a ball up a steep road. Alright, so what I have, let's make a list of what I know. Okay, so it leaves her foot at 28, so that's V initial. Encounters a downhill acceleration, so I have A. It's rolling back to her at, I have V final. How long ago did she kick it? That's time. Hey, look at that. I'm just going to use this same equation again. And I just had to remember that when it's rolling back towards her, that has to be a negative velocity. So the final velocity is negative 17. The initial velocity is positive 28. And since it's going to slow down and then come back, I have to make this a negative 5.8 acceleration. So, number 7. Let's move this up a little bit. Alright, in the diagram above, the oil drops fell once every second. So you've got to keep in mind with an oil drop that these are time intervals. These both have the same time intervals. They just have different distances. Okay, so each grid line equals 1 meter. Which object traveled at a constant velocity? I think most of you will be able to look at it and see B traveled at a constant velocity. And if I want to know what that velocity is, I just have to remember that is going 1, 2, 3, 4, 1, 2, 3. It goes 4 meters every second, which gives me 4 meters per second. Now for the second one, which object is accelerating, you can see that A starts off slow and gets faster and faster and faster. So I would just simply use the equation D equals 1/2 AT squared. Since it started from rest, I can do that. And I'm going to solve that for A. And although I didn't mean for it to work out that way, it turns out to be 1 meter per second. So I mean, basically I would look at this and I'd say, well, I'm going to pick a nice easy one. So I'm going to say there's 1, 2, remember this is time 0, so I have 1, 2, 3, 4 seconds, and that distance is 1, 2, 3, 4, 5, 6, that's 8 meters. So I'll put 8 meters here, I'll put 4 seconds here, and when I solve for A, I get 1. Now number 8 in the diagram above, how long did the object travel at constant velocity? Well, from time 0, for 1 second it went 4, for the second it went 4, so now we're at 2 seconds, 3 seconds it still went 4, 4 seconds it still went 4, so sometime after 4 it slowed down, so we know for sure 4 seconds, so let's just go with that. Okay, let's see, during which time interval was the object speeding up? So if you're speeding up, that means that you have an acceleration that is causing you to have a steeper slope. So you might be tempted at first to choose this one, to choose this one here, but that's actually going towards a flat slope. Where at here it's 0. Remember, this on a distance time graph, the slope of the line is how fast you're going. So I was going at a certain velocity and I slowed down to 0, stayed 0, and then I began to speed up in the negative direction. So this is the answer here, so from time 15 to 18. During which time interval was the object slowing down? Well, it'd be right in here is where it's slowing down, because it had this velocity and it slowed down and stopped. So basically from 5 to 10. Now for C, during which time interval was it stationary? That's this time interval here. From 10 to 15 it's stationary. For D, at what time was its velocity? What was its average velocity during the first 5 seconds? Well, I'm basically going to take the change in distance. So I'm going from negative 10 to positive 6. So that's 16. 16 divided by 5 gives me 3.2 meters per second in the positive direction. what was the object's average velocity during the time interval 15 to 18? So now remember, average velocity, you just take the beginning and the end, right? That's how we're going to find it. We're going to say you started here, you ended here. So how much did we delta our x? Well, we deltaed our x by -6 meters. And we did that in 3 seconds. So that gives us -2 meters per second. Oops, yeah. All right, and number F. number F. Let's see. So F, did the object have a positive or negative velocity values during the time interval 5 to 10 seconds? Was its velocity positive or negative during the time interval? Oh, that's terrible. That's a mistake. It had a positive velocity here. Oh, darn. Look, I put the wrong answer here. I feel terrible. It had a negative acceleration here, but it had a positive velocity. So actually the answer is positive. I feel terrible. It is definitely moving in the positive direction between these 2 points. I am so sorry that I made that mistake. Alright, let's keep going. The graph above depicts a ball that an astronaut on a cliff, alien planet, reaches time 0. What is the acceleration of gravity on this planet? Well, to find the acceleration of gravity, you simply find the slope of the line. So, the easiest way, I think, would be to say, well, we started off at 40, and we reached a velocity of 0 after 8 seconds. So, I have a change of -40, and it took 8 seconds. And that gives me -5 meters per second squared. Was the ball thrown up or downwards? Now remember, if I throw a ball upwards, it starts off moving in the positive direction, so it has a positive velocity. So if the ball was thrown downwards, it would have started off here with a negative. If it had been released without being thrown, it would have started off here. But anytime you look at a motion graph of velocity versus time, and you start off here, you know the object initially had a positive velocity. It was thrown upwards. So up. When did the ball reach its highest point? Well, it's going to go up and it's going to reach 0 and then come back down. So it reached 0 in 8 seconds. When did the ball pass by the astronaut? Well, it went up for 8 seconds, so 8 seconds later it's going to pass by the astronaut, so that would be at time 16. And at what time did the ball touch the ground? Well, when it hits the ground, it bounces, so it has a very brief, very sharp positive acceleration. So that looks to me about time 20. And what was the ball doing at the 26 second mark? Well, it leaves the ground with this positive velocity, and it basically slows down on its way up, and then it reaches its apex, and it's going 0 at its apex, so it's at the apex of its bounce. For the graph above, what was the starting velocity? It looks to me like we start off at positive 20. The ending velocity was -30. And the acceleration, well, I just say the total change in y is going to be, let's see, we ended up with, let me just switch over, so we ended up at -30. So I have -30 minus 20. That gives me a change of -50 meters per second. And I did that in 10 seconds, which gives me -5 meters per second squared. To find the displacement, what you have to do is you have to calculate this area here and then this area here. Now this is going to have a positive value and this is going to be a negative value. So here I'm going to say 20 times 4 divided by 2. 20 times 4 divided by 2. That gives me an area here of positive 40. So I have positive 40, and when I do this one here, I'm going to say from here to here is 6, from here to here is -30. 6 times -30 divided by 2 is going to give me -90. And when I combine those two displacements, first I was displaced positive 40, then I was displaced -90. When you look at my total displacement, it's -50. Alright, so here I have a velocity time graph. And remember, velocity is meters per second and time is second. If you multiply, as in finding the area of one times the other, if you take meters per second, which is velocity, and you multiply it by seconds, the seconds cancel out, and they just leave you with meters. So the idea is you can find what we call the area under the curve, so the area between the line and the 0 line. So first I'm going to find the area of this part of the graph, and that's basically going to be negative 20 times 2 divided by 2. So that gives me negative 20. So I'll say negative 20. And then I'll find the area of this part here. So that's 10, 20, 30 times, I'm sorry, 1, 2, 3 times 10, 20, 30. So that would basically be, this area is 90, so half of that is positive 45. I use blue for positive. And then I'm going to do the next area. This area here is 30 by 1, 2, 3, 4, 5. So that's 150. So I have positive 195 minus 20. So I have positive 195 minus 20. And what it gives me is positive 175 meters. That's a 5, unfortunately. So now if I look at the next one, if I start off 20 meters to the left, 80 meters to the left of you, basically what I'm saying then is we're starting off at negative 80 meters. And we're displacing 175 meters in the positive direction. So if I say negative 80 and add 175 to it, I get 95 to the right in the positive direction. Let's try next one. Alright, how fast was the object going at the end of time? Now in this case, with an acceleration versus time graph, if you find the area by multiplying y times x to find the area, what you're going to find is you're multiplying meters per second squared times seconds. So this second cancels out one of those, leaving me with meters per second. So what it tells me is the change in velocity. How much did the velocity change by undergoing these accelerations? So what I'm going to find then is, let's just use blue for positive again. So first I'm going to say 20 times 3, that's positive 60. And the nice thing about acceleration graphs is, at least in AP Physics, they're always going to be flat. And now here I have negative 20, and here I have positive 90, and here I have negative 40. So I have a total of negative 60, and I have a total of positive 150. So that gives me positive 90 meters per second of change. The delta V is 90 meters per second. You end up going 90 meters per second faster than you were before, or at least accelerating. You have a positive acceleration of 90 meters per second. Now, if the object started off going 25 meters to the left, and it has a positive 90 meters per second acceleration, I'm basically going to do what I did up here. I'm just going to say, well, this is negative 25 plus 90. That gives me 65 meters in a positive meters per second in the positive direction. If the object started off at negative 100, at what time did it stop moving to the left? I'm sorry, I didn't mean it to work out this way. But if I take negative 100 and I add 90 to it, I'm still going this way at negative 10. So it never stopped. I wanted to stop somewhere in here, but I just screwed that up. Sorry. Let's keep going. Here's a good one. This one comes actually. I took this one from an AP Physics released item here. So the diagram represents 28 seconds, at which time was the car at rest. So on a velocity, you've got to remember, you've got to first look and see what your axes are. And on the AP test, they like to put the axes labels here, I've noticed. So I put them here to mimic that. So this is velocity. These are meters per second. These are not distances, these are velocities. So remember, on a velocity versus time graph, if you're not moving, if you're at rest, what's your velocity? Well, it's 0. So the times would be here and here. And that would be 6 and 19. During which time intervals was the speedometer reading increasing? This is just its speed. When is its speed increasing? Now, speed is not a vector. It doesn't know about direction. It is direction ignorant, remember? So what that means then is, if your velocity is basically changing. So if you look here, I'm at this point here, I'm slowing down towards 0. So right there, that's not. I mean, I might have a positive slope, but my speedometer say I'm going what, like 9, and I was going to slow down. And at this point, it says I'm going 0. But from this point to this point, from 6 to 9, I go from 0 meters per second to 4 meters per second. I'm speeding up. Here, I'm staying at 4. I'm not speeding up. Here, I'm going from 4 down to 0. I'm still not speeding up. But at this point here, I'm at 0, and now I end up at something bigger than 0. So between 19 and 23, I'm speeding up. Then I keep the same speed, and then again, I'm moving away from 0. My speedometer needle is moving away from 0, so I'm speeding up, and that gives me this one here between between 25 and 28. I can see how you get tricked by that. But that's really what they want to see. Do you understand that this is 0 velocity, and if you move away from it in either direction, you're going faster? Now, let's look at this next one. If the car started out at a location of x equals 5, where did it end up at 10 seconds? Now, the way you're going to solve this next one is you're going to find the area under the curve, because remember, if you're dealing with a velocity versus time graph, the trick to it is find the area under the curve to find displacement, because meters per second times seconds gives you meters. So what I'm going to do is I'm first going to calculate the area here, and when I do, I'm going to get negative 24. And then I'm going to calculate the area here on this triangle, and I'm going to get positive 6. And I'm going to have to calculate the area of this little rectangle here, and I'm going to get 4. So what I have is a total of positive 10 and negative 24, so the net change is negative 14 meters. So if I start off at a position of positive 5 and I displace in a negative direction 14, it gives me negative 9 meters. Oh, I know how much you love these. Alright, let's try this. The way to look at this is on a distance versus time graph, the slope is how fast you're going. A steep slope, whether it is in a negative direction or a positive direction, it means you're going fast, and a flat slope, like here and here and here and here, means you have a velocity of 0. So here I have a fairly large velocity in a negative direction that ends up being 0. So I start off with a negative velocity that's fairly large, and as time goes by I reach a velocity of 0, because this is velocity and this is the 0 line. Now I'm at 0. Now I'm developing a positive velocity, and it's getting steeper. It's increasing in that direction. So here I'm moving to the positive velocity area, because this is the positive part of the graph, and it's getting greater. Now, let's see. At first I am slowing down in the negative direction, then I'm speeding up in the positive direction. That's called a positive acceleration. Let's try our next one. We start off with a velocity that is a displacement line that is flat. That means my velocity is 0, it's very high, and it's back to 0. That's really how you want to look at it. I'm 0 here, I'm fast here, I'm 0 here. Now, I start off with an upward slope. That's a positive velocity. I'm displacing the positive direction, and I'm starting off slow and getting faster and faster and faster. I reach my maximum velocity, and now I'm going to begin to slow down. I still have a positive slope. I'm still moving upwards. The whole thing trends upwards. So I still have a positive velocity, but I end up with a velocity of 0. So I start with a high velocity that's positive, and I end up at 0. Now, here I am getting faster in the positive direction. That's called a positive acceleration. And at this point, I begin to go slower in the positive direction. That's called a negative acceleration. So I get a graph that looks like that. Let's look at our next one. Don't worry, I'm only going to give you one of these on the test. I know they're hard, but they're important to do. They really help you understand the difference between velocity, acceleration, and distance. Alright, so here we go. Now I start off and I have a fairly steep slope that goes towards 0, but it's steep in the positive direction. So I have a positive velocity that's fairly significant right here. It's positive and it's far from 0. At the dashed line, my slope has gotten flat, so my slope is now 0. So I went from a high positive velocity to a velocity of 0. Now look, right now I'm at 0, but I'm going to get faster and faster and faster in the negative direction. So I have a negative velocity that's getting bigger. I have a negative velocity and it's getting bigger. Now the slope never changed and the slope was always negative, so I have a negative acceleration. This next one, I start off, I have a constant velocity that is in the negative direction. So I have a constant velocity, I'm in the negative direction, and my velocity is constant and it's negative. Now when I get to the dashed line, I begin to slow down in the negative direction. If you're slowing down in the negative direction, you have a positive. So basically, here's what it means is I'm still in the negative, but I'm trending towards a flat line, which is a velocity of 0. Now I'm moving towards a velocity of 0. Now in terms of acceleration, I am not accelerating here. I'm moving at constant velocity. I have no acceleration. At this point here, I begin to slow down in the negative direction, which if we continue on, that makes you speed up in the positive, so that is what a positive acceleration looks like. Car pulls onto the highway, it accelerates, it goes from 8.4 to constant, okay. How fast is the car going before it began to accelerate? So this is a kinematics equation one here, so we had to figure out which of our big four equations are going to work. So that means I'm going to make a list of what I know. I know that I have meters per second squared is my acceleration. I have the amount of time it took, and I know that let's see, the final velocity is this, and I want to know how fast it was going before, so that would be v naught. So what I ask myself is, what equation do I have in my tool chest that uses velocity, acceleration, time, and solves for v naught? Well, that would be big equation 1. That would be v equals v naught plus acceleration times time. And I'm just going to substitute in the appropriate values. So 44 goes here, 2.2 goes here, 8.4 goes here, and then I'm going to solve for v naught, and I get 25.5 meters per second. Our next one, again, it looks like a kinematics problem, so I'm going to make an inventory of what I know. The hot air balloon is traveling upwards at 12, so here I have v naught. And a person drops a balloon out of it. How far? So I'm looking for how far is a delta x. I'm looking for a change in. I'm looking for displacement. How far does the water balloon have to fall in order to reach a downward velocity of? So here I have a v final. And one thing that's not mentioned here is I'm probably on Earth, so I do know my acceleration equals negative 10 meters per second squared. So let's see, what I have here is I'm looking for displacement. I have v initial, v final, and acceleration. That would be this kinematics equation here. V squared equals v naught squared plus 2a, I'll just write delta x. You could write parentheses x minus x naught if you wanted to. So I'm just going to substitute into these. I'm going to say, well, let's see, 12 goes here. Now this is actually negative 33, but in this equation you're going to square it and it's not going to make any difference. And then 2 times negative 10, don't forget this is negative, that will give me my displacement. So I displace in a negative direction courtesy of my negative acceleration here. A baseball is seen to pass by a window at 25 meters, so that is delta x, or x final really. X initial is 0, we would assume, above the ground at 12 meters per second, so that's how fast it ended up going, so that's v. And the baseball is thrown, what's its initial velocity? I don't know, but I do know acceleration equals negative 10. So once again, I'm going to use this exact same kinematics equation, except this time I'm going to solve for v naught, and when I do, I get 25.4. Worker drops a hammer off a building. Okay, so what I see is it goes past the first window, at 35, so I'll make that V initial, and it goes past one later, I'll make that V final. I want to know what the distance is, so that's going to be delta x. I know A is negative 10. I'm using that same darn one. I should be more creative than that. So that's going to be V squared equals V naught squared plus 2A delta x. And in this case, I'm solving for delta x. And when I do, I get negative 243. A bullet is dropped into a river off a very high bridge. At the same time, another bullet is fired upwards from a gun. So let's see. Neglecting air resistance, the acceleration. Be careful here. This is a classic trap question in physics. Is you've got to be careful. Acceleration doesn't change. That's really. It's not that they're trying to trick you when we ask these questions. It's just we want you to understand that acceleration is independent of your velocity and it's independent of time. The acceleration is uniform, so it's the same for both bullets. The moment it is shot upwards or downwards or sideways or anyway, as soon as it is in the air, it is going to begin to accelerate downwards at negative 10 meters per second squared. Now, someone standing on the edge of a cliff throws one ball straight up, another one straight down. Neglecting air resistance, the ball to hit the ground below the cliff with great speed will be, well, here's a way to think of it. If I throw it up at 40, how fast is it going to be going when it comes back to me? It's going to be going down at 40. And if I threw it down at 40, or it went up and came down at 40, it doesn't matter. It still hits the ground at the same speed. This one I threw down at 40, and this one went up and then came back down at 40. So the answer is neither. They'll be the same. If a ball is thrown upwards, how long will it have to? How long will it remain in? What speed does it need to be thrown to remain in the air for 10 seconds? So it's going to go up for 5 and down for 5. So in order to get something to go up for 5, if it's slowing down 10 meters per second every second, I need to throw it up at 50. So it's going to go up 50, 40, 30, 20, 10, 0, 10, 20, 30, 40, 50. It's in the air for 10 seconds. Guys, you're going to see one like 23. I got to tell you, this is such a classic question. We did a lab with it. I've given you a million questions with it. The trick to these is you use the vertical distance to find time. You're going to use this one right here, and you're going to say d equals 1/2 at squared, and you're going to use that to find the time. Okay? And if I do that for this one here, if I say 1.2, let me just take out my calculator and do this real quick. Even though I'm recording, I'm going to say the square root of 1.2 divided by 5 is going to be in the air for 0.49 seconds. So the time here is 0.49 seconds. That's how long it's going to be in the air for. And at 0.49 seconds, it's going to travel and it's going to land 3.8 meters away. So then, to solve for a horizontal one, always for solving horizontal, the only equation for horizontal is velocity equals delta x over t. And the reason is, this is the one equation we have in kinematics that does not involve acceleration. It's the only one. So horizontally, when we neglect air friction, there's no acceleration. So therefore we use this equation. Now, I know delta x is 3.8. I now know that time is 0.49. So 3.8 divided by 0.49 gives me 7.8 meters per second. You're going to see one of these on the test, so please figure this one out. Alright, the next one, a rock is dropped off a high bridge. How long does it take to reach the bottom? Well, if it's, if I'm 160 meters up, I'm just going to use d equals 1/2 at squared. This is d. I know what a is, so basically what I do is I have to take to solve that, I'm just going to say the square root of 160 over 5 equals t. And when I do that, what I get is 5.7 seconds. So now I know my rock fell for 5.7 seconds. How fast will it be going when it reaches the bottom? Well, it picks up 10 meters per second every second, so it's going to hit 10 times faster than that, 57 meters per second. Do you hear my dog breathing over there? He's so loud. What is the rock's acceleration? There's that trap question again. You know what? If it's accelerating because of gravity, it's negative 10 meters per second squared on Earth. How long would the rock have fallen if the bridge had been twice as high? So remember, if I double the height, what I do then is I say, well, double the height. So d equals 1/2 at squared. So the way to think of this is d is proportional to t squared. So if I double the d, and I want to know what the t is, to find the t I had to take the square root. So really what I'm doing is I'm taking the square root of 2, which is 1.4. It's going to be 1.4 times faster, longer rather. So I'm going to take 5.7, I'm going to multiply it by 1.4, 5.7 times 1.4, and that gives me 8 seconds. A water balloon is dropped out of the 5th floor window. Which floor do you have to drop the balloon in order for it to 3 times the velocity? So if I take the velocity and I make it 3, basically, if I triple the time, I triple the velocity. So therefore, if it's triple the velocity, it fell 3 times farther, I'm going to say 3 squared is 9, and 9 times 5 is 45. An astronaut throws a rock upwards, it goes 30. He throws another one half as fast, so that's 0.5. So what I do is again, think of fast as how much time. Because if I throw it twice as fast as in there, twice as long, half as fast in there, half as long, 0.5 squared is 0.25. So I'm going to multiply 30 by 0.25, and I get 7.5 meters. Ball is kicked in such a way that it has 28 vertical and 12 horizontal. How long will it be in the air? That's all about vertical. The amount of time something's in the air is only about its vertical components, either the vertical velocity or the vertical distance, as in the case up here. So if it's going up at 28 meters per second, it's going to go up for 2.8 because it's slowing down at 10, and it's going to come back down for 2.8, which puts it in the air for 5.6 seconds. How far away is a horizontal value? Remember, for a horizontal value, the only equation I can use is v equals delta x over t. Now I want to know how far away. That's delta x. So what I'm going to do is I'm going to say 12 meters per second, which is its horizontal velocity. So 12 goes here, and for time I'm going to put 5.6 here. I end up multiplying those, I get 67.2 meters. How high it will go, that's vertical. So this is the vertical information I've been given. It's going to go up for 2.8 seconds. Be careful, it's not going to go up for 5.6. It's going to go up for half of that. So I'm going to take 2.6. I'm going to use d equals 1/2 at squared, but I'm going to use 2.8 seconds. Oops. And I'm going to put that in there for time. So I'm going to square this and multiply it by half of a, and it gives me this. What is the launch velocity as it left the kicker's foot? So in order to do this, I have to use Pythagorean theorem, and I have to add vectors tip to tail. So I start at the origin, I go, okay, I'm going to go horizontally for 12. Now I'm going to go up for 28. And I want to find what this is. That's how fast it left the kicker's foot. Because if you think about it, this is the cosine of this, and this is the sine of this. So take these two, and that gives me what this is. And if you say the square root of this squared plus this squared, you get 30.4. Now if I want to know the angle it was kicked at, now I have to use a little bit of trig and say, whoops, I'm basically solving for theta, right? And so if what I know for sure, I could use this value, but that's a calculated value, and there's some rounding errors in here, so I'm going to use the original values. So I'm basically going to use tangent equals, so basically I'm going to say tangent of theta equals opposite over adjacent. And now I'm going to solve that for theta. So basically what I'm going to do is I'm going to take this, I'm going to take the inverse tangent of this, and it gives me 67. Alright, ball is kicked at 65 degrees. When you're given a degree, first thing you want to do, check your calculators and make sure you're in degrees. I'll remind you that at the start of the test, but you want to go into the check your mode and make sure that you're in degrees, not radians. We'll use radians later in the year. So, if it leaves at this velocity and this angle, here's what I'm going to do. I'm going to find the vertical by taking the sine of 65 and multiplying it by 32. All right? And to find the horizontal component, I'm going to take the launch velocity and I'm going to multiply it by the cosine of 65. And so when I do that, I get these two values. I get a vertical, that's what I use the sine for, of 29. I take the cosine of 65 and multiply it by the kick velocity, and I get 13.5. How long is it in the air? That's the vertical that determines it. So if it leaves my foot at 2.9, it's going to go up for 29. It's going to go up for 2.9 and down for 2.9, accelerating at 10 the whole time, and that puts it in the air for 5.8 seconds. How far away is a horizontal value? I have to use the horizontal component of velocity, and I have to use the equation v equals delta x over t and solve it for delta x. So what I'm going to use is the total time in the air, because the whole time it's in the air it's moving horizontally. So I'm going to say 5.8 seconds times 13.5, and that gives me 78.3. How high it goes is a function of the amount of time it climbed up for. So since it left at 29, it's going to go up for 2.9 seconds. And to solve for vertical distances, I equals 1/2 at squared. So 2.9 squared times 5 gives me 42. Arrow shot upwards at an angle of 50, leaves a bow at 45, lands on a cliff 4.5, on the top of a cliff 4.5 seconds later. So I'm going to draw this. So basically I have this situation here, and the arrow is doing this. And it came out of here at a 50-degree angle at 45 meters per second. Alright, so the first thing I do is I got to find the sine and cosine of this. Alright, so I'm going to take 45 times the sine of 50 gives me the vertical velocity. 45 times the cosine of this gives me the horizontal. Let me just go ahead and calculate. So now I calculate, here's what I find, that the vertical component is basically 34 and a half, I'll just say 34. And the horizontal component is 29. Which we shouldn't be surprised that the vertical is greater because the angle is above 45. So it's going to go more up than it is out. Now, how high the cliff is, I got to be careful here because I have a delta x now. So I'm going to have to use this kinematic equation here. I'm going to have to say that x equals x naught plus v naught t plus 1/2 at squared. I'm going to have to use that equation. I'm going to substitute in where this is 0, because we're assuming it's launched from 0 height. I could have made it a little more complicated and told you exactly how high it leaves. This is the height of the cliff that we're looking for. V naught is how fast it left the bow vertically, so that's going to be 34, not 45, because the vertical component is because it only accelerates in the vertical direction. So I have to use 34 over here. The time it's in the air for is 4.5 seconds, so I'm going to put 4.5 here. And then A is -10. Let's just substitute so you see what I'm talking about here. So I'm just going to do this. So we'd say x equals 0 plus positive 34 meters per second times the time it's in the air, which is 4.5 seconds, plus 1/2 of -10. Don't forget the negative, my friends, times 4.5 squared. And if you run your numbers through there, here's what you're going to come up with. That cliff is 54 meters tall. The trick is, remember, acceleration is negative, and it's the vertical component of velocity that I use. Now, how far away did it land? Well, all I had to do there, this is always an easy question. The horizontal component is 29, and the total time in the air is 4.5. So I multiply 4.5 times 29 gives me 130. Oh, I like these next two. A precious glass figurine is launched at, so the first thing I do is figure out how long is this thing in the air for, and let's see. So, and where is it going to land? So the first thing I got to do when I have a problem like this is I had to figure out what is the vertical and horizontal component. So the vertical component I would find by taking the launch velocity times the sine of 60. That gives me vertical. Sine gives me vertical. So 40 times sine of 60 gives me a vertical of 34.64 meters per second. And it gives me a horizontal component of velocity of exactly 20 meters per second. So the idea then is, how long after launch did she catch it? It's got to go up for 3.464 seconds and down for 3.464 seconds, which puts it in the air for 6.9 seconds. Now, in 6.9 seconds of being in the air, how far downrange is it going to travel? Well, it's going to travel 20 meters every one of those seconds. So for 6.9 seconds, it's going to travel 20 meters every one of those seconds, which puts it 138 meters away. Now, this person on the motorcycle needs to catch up to it. So if I want to figure that out, what I do is I use this as the distance she's got to go to catch it. I know she's going to go this distance. She has this long to get there. So I'm going to say, I'm going to use d equals 1/2 at squared. I'm going to square the time. Here's my distance, and I'm going to solve for a. I get 5.8 meters per second squared. And how fast will she be going? Well, she accelerates at 5.8 meters per second squared, and she does that for 6.9 seconds. She ends up going 40 meters per second. That's a cool problem, I think. Not as cool as this next one, although I had no idea it was going to work out to be 10 meters per second squared. That's just crazy. All right, Superman is flying, sees a worker fall off a tall building. All right, I know how far away Superman. You know what? Let's draw a sketch of this so we know what we're doing here. Okay, first let's move this up. Okay, so I'm going to make a sketch. Okay, I have a building here. All right, I have a worker falling off the building. Whoa. This building is 80 meters tall. All right, and I know that I got Superman is going to fly and catch him. Now he's going to look like he's running into the building, but actually he's going a different direction. So Superman is 200 meters away. He's flying initially at 30 meters per second. And what I want to know is, how fast does he need to accelerate? So I'm looking for his acceleration if he's going to catch that man before he hits. Well, you know what I know? I have a vertical distance here, and so I can figure out how long it takes to fall. And if I use d equals 1/2 at squared for 80 meters, the person's falling for a whopping 4 seconds. So now, here's what I got. I'm going to use this kinematics equation here. I'm going to say x equals x naught plus v naught times t plus 1/2 at squared. So I am looking for, let's just say I'm looking for how fast he has to accelerate. So I'm looking for the a in this equation. So the x that Superman is going to fly, he's going to go 200 meters, starting at his initial position, which we'll call 0, plus he was originally flying at 30 meters per second. Now he accelerated we calculated 4 seconds is how long the guy fell for, plus 1/2 of his acceleration times the square of 4. And if I solve that equation, remarkably, although I didn't intend it to be, you get 10 meters per second squared. He's got to accelerate at 1g. Hey, please study for your test. I really want you to all make A's. See ya on Tuesday.